I have the tremendous pleasure and the big honor here to introduce you to Clifford. For the most of the guys who know him and the other guys who don't know him, be warned, because this man is like a bullet train. So the moment we press that button, start, he starts a race, and you be careful. So fasten seatbelts, ladies and gentlemen. Here's the man.
Thank you.
Yes, light the fuse, put it in play.
So, okay, this is my talk about formal verification with Yosys SMTBMC. And it's the... This is my talk about formal verification with Yosys SMTBMC. And it's a shorter version of my talk, but I still need to speak very fast. So if you're interested in the full slide set, go to this link. The link will be also on the last slide of this presentation, so you don't need to write it down right now. And you can also download all the example files for all the examples I'll show you during my talk from this page. And my goal is really to just give you rough idea of what you can do with Yosys SMTBMC, and then you can download these example files, reproduce the stuff that I will be talking here, and then modify these examples to fit your verification needs, whatever you need to do. Okay, but really quickly first a little bit about Yosys as a whole, because there are a lot of things you can do with Yosys besides formal verification. So there are a lot of synthesis flows that are available in Yosys. So most prominently, we can do synthesis for ICE40 FPGAs. I had a talk last year at CCC about that, and I had to reverse engineer the ICE40 bitstream format in order to enable this flow. But there is also a synthesis flow for Xilinx 7 series FPGAs. Here you need to use Xilinx Vivado for place and route, but the synthesis part can be done by Yosys. There are also a couple of ASIC flows that are enabled by Yosys. You can also do your custom synthesis flows, which is something that some people do. On the formal verification side, we have Yosys SMTBMC, which is the thing that I'll be talking about today. But there are also some other verification flows available in Yosys. For example, there are a couple of built-in commands in Yosys directly that can be used for certain verification tasks. There's a built-in SAT solver that you can use for some things. There is an equivalence checking framework. Or you can use Yosys just as a front end to convert your design into something that can be understood by other tools. For example, you could use Yosys as a front end and combine it with ABC and do verification in ABC. But the thing I'll be talking about is the first one, Yosys SMTBMC, a framework for bounded model check and temporal induction enabled by Yosys. It can be combined with any existing SMT-lib2 solver. So there is not a lock-in here to one specific solver. You can combine it with anyone, because I'm using the SMT-lib2 language to communicate with that solver. And there are a couple of solvers that are well-tested. So usually when you read here supported solvers, it means well-tested solvers, because in principle it should work with any solver that supports this file format. And those well-tested solvers are, for example, Z3, CVC for Yikes, and so on. Good, but before we dive into formal verification, I have this slide. And this is why you should be excited about this slide. So I have some thoughts here about the availability of ADA tools for students, for hobbyists, for enthusiasts who just would like to experiment with the technology, all that kind of stuff. And on the FPGA synthesis side, there are a couple of free-to-use tools. So if you're interested in playing with this kind of technologies, you can just download the free stuff from Xilinx or Altera or any other vendor and install it, and maybe within an hour or two, if the installation goes without any major difficulties, you you can play around with it and you can start making your experiences with this kind of technology. And with FPGA synthesis, there are even some free and open source options. So there is the Yosys flow with Project iStorm for IS-40, for example. But this is not the only one. There is also VTR with Odin 2 as Verilog framework. So there are a couple of options there. The same thing for HDL simulation. If you would like to simulate a circuit, or if you would like to make your own experiences with FPGA or HDL simulation, you can download some free-to-use tools like Xilinx XSim. And there are even some open source tools that you can download and start learning about this kind of stuff just within minutes, how long it takes to install Icarus Verilog using apt-get or something like this. However, on the formal verification side, we have a completely different picture. There's practically no free-to-use tool. There is, besides the things I'll show you today, no free and open source tool that you could use to do end-to-end formal verification. And interestingly, at the same time, people in the industry are complaining. They can't hire anyone who has experience with formal verification. And I really wonder why this is so, why there are no people with formal verification, even though the industry demands them. So I think this should be the focus of that. I can't really tell you stuff like how fast is my flow compared with the commercial flows, because I don't have access to those commercial flows. I had no way so far to compare my stuff with the commercially available stuff, because even though I do some research at the University Institute and I have some commercial software there, I have nothing that's comparable on the formal verification front. So I think it doesn't really matter that much if my tool is faster than the commercial tool, if it supports exactly the same feature set. The really important thing is that this is something that enables you to make experiences with this kind of technology. And hopefully, one day I will be able to compare my work with the commercial tools, and then I will know if I'm better, or if they are better, or if they're about equal. Okay, so when we're talking about formal verification, what are we actually talking about? And in almost all presentations about this kind of stuff, you will find a slide that looks more like this one, where we have a couple of states your circuit can be in, and a couple of simulation traces. So the simulation traces are the, I don't know what color this is, but this here is a simulation trace. Oh, you don't see it. This here is one of those simulation traces. And you see we have 3 simulation traces here, and they cover a subset of all the reachable states. Interestingly, they don't cover this red state, and the red state is a reachable state that violates an assertion. So when we would like to verify this circuit, we would like to be sure that we have caught this red state, that we have shown that this state is actually reachable. One way to improve the coverage here would be just to run more and more random simulations, right? However, if you look at this example really carefully, you will see that there is only one possible path that goes to this one red state. And one of those traces almost got there, but in the last minute it decided to go a different route within the state diagram. And if you just multiply the choices you have at each node on this path, you will realize that you could run 1,000 simulation traces on this really, really small example, and you still only have about 50% chance to get to this one red state that violates your assertions. So random simulation is not really a solution. If you would like to make sure if an invalid state is reachable or not, you have to use formal methods. And the formal methods actually look at the whole state diagram as a whole. So it's not simulating many individual traces. Instead, it will give you a definite answer if this state, this red state, is reachable or not in this situation. And when you simulate it a lot, you can be fairly certain, you can be more certain if you simulate for many hours, but only with formal verification you can absolutely be sure that no assertion can be violated in your design. So that's what we're talking about when we're talking about formal verification. So why would we do this? Why would we want formal verification? And in almost all cases where people use formal verification, they have the first use case. They would like to prove that a design is correct. And in many cases, this is a really good reason to do formal verification. I just told you, when you have to be sure, this is the only way how you can achieve that. However, proving that a design is correct, even if you have a formal verification tool, is a pretty hard thing. So first of all, you need a formal specification of the correct behavior. If you don't have a formal verification of the correct behavior, how can the tool know which is the right behavior and which is the wrong behavior? And usually, just this one step, creating a formal specification of the right behavior, can already be a showstopper. This could be a project so large you wouldn't think it's worth your while in many applications. So maybe if you in some space applications, you can't get around it, but in many other cases, people might say, well, if there is a problem in the field, I'll just create a new FPGA image and we will figure out how to update the devices in the field. However, there are two other big application domains for formal verification. There is bug hunting and there is optimization. And I think usually we don't talk about these two that much. And I think the reason is that the pricing on the commercial tools is so prohibitive. So you only buy those commercial tools if you really have to. And the only case where you really have to is if you have the first case, if you need to prove that the design is correct. And many projects might benefit from having formal verification around for bug hunting or optimization, but they don't do it because it's not on the radar. So what is the difference between bug hunting and proving that the design is correct? So first of all, for bug hunting, you only need a partial specification. If you just have specified some part of the circuit, you can use the formal tools to figure out if the circuit at least conforms to this partial specification. Maybe there is other stuff that is not specified with this partial specification, but if there is a bug that is somewhere within the specified domain, then you can use this. The other thing is, when you do bug hunting, you can do many different checks with different overlapping partial specifications. And you only need to have a really good feeling about that all these overlapping specifications really cover the entire behavior of the circuit. Whereas when you would like to prove that the design is correct and you would like to fracture it into individual small checks, then you have to have a second proof that proves that you haven't left any gaps with this partial specifications. And there are cases where people do that and they claim they do the first thing, but actually they don't, because this are questions that are left open if you do that. So this is just bug hunting. But it can be really beneficial to have those tools for bug hunting. Usually they will find bizarre bugs, really obscure bugs that you would never find using handwritten test benches, because nobody comes up with the crazy things they do with your design in order to trigger an assertion. So not only will it find bugs, it will find those bugs that are really hard to find in the field. The bugs where you have a processor and it works really fine, and after a year that is in the field, someone comes to you and says, well, there is this one GIMP plugin, and if you use this binary for this GIMP plugin, and you run it an entire day, then it will somehow crash the processor at one point. And this is like the thing you get as a bug report, and then you have to figure out how to go from there to the one obscure thing in your instruction cache that went wrong and that was triggered by this one scenario. But But if you find the same bug here, the tool will give you a counter example, will tell you, well, if I use the inputs of your circuit in this way, then the circuit will go into this state, and here you have said this state is an invalid state that should not be readable. So you're in a much, much better position to figure out what's actually going wrong. Even if you could already reproduce the bug in hardware, you would be on a very different standing here. So be the hunter, don't be the hunted when it comes to bugs. With optimization, we essentially do the same thing as we would do when we prove a design is correct, but we just use the unoptimized design like a spec. So we have already a design that works, and we know this is the behavior we want, and now we would like to optimize the core, and usually when you optimize a core, you make it a little bit more complex. So if you would like to optimize for power, for example, you would add clock gating in certain cases, and then you have to put additional thought into which flip-flop stage can be clock gated in which cycle, and if there is a problem somewhere, then you would find this by formally verifying your optimized design using the unoptimized design as specification. In this case, this would be very, very similar to formal equivalence checking. However, there are cases where your optimization reduces the number of cycles needed to produce the same result. And then we are already beyond what formal equivalence checking would do, because now we have two circuits that are formally not equivalent, because one circuit is producing the result one cycle earlier than the other one, but we could still construct a formal proof using property checking to make sure that the result both circuits produce are the same. Okay, I'm not really going to talk about the things on the slide here. This is just to show you it's really easy to install this on Ubuntu or any Debian, also other distributions, of course. So you really have no excuse not trying this out. If you do anything where formal verification could be useful, it's not like you have to spend an afternoon compiling Fortran code from the 70s. Instead, you just get some prerequisites, and then you build Yosys, and then you build an SMT solver, and after 20 minutes or however fast your computer can build large C++ projects, you have everything installed, and you can playing around with the examples in this presentation. The first link here is the same link we had on the first slide. This is where you can download the slides and also some example files. Some example files that can also be interesting are the examples in examples/SMTBMC within the Yosys source code. And if you know my Pico R32 project, it's a RISC-V implementation. There is a couple of formal stuff there as well, and you could also look there for more examples and crazy things you can do with this formal verification flow. Okay, let's get right into it. Some code. This is a simple hello world example. So we have a counter. We initialize the counter to 0 in this case. And then we have a clocked block, and we say whenever we get a rising clock edge, when reset is high, then counter will be set to 0. And when reset is not high, then we will increment the counter. And then we have some formal statements at the end of this input. So we assume that the counter will never reach the value 10. And then we assert that the counter will never reach the value 15. And since we are incrementing in steps of 1, we never can go to 15 without going over 10. So indeed, this should hold. To verify this, we call this 3 commands on the lower right. The first command is Yosys. So we use Yosys for synthesis of this circuit, but we don't synthesize this for an FPGA or an ASIC architecture. Instead, we synthesize it into an SMT2 description of this circuit. And then we use Yosys SMTBMC to check if the assertions are right. And we have two calls here. The first one does a bounded model check. So we check if the circuit, if all the assertions hold within the first n cycles. The default value is 20. And the second call tries to perform an induction step to prove that, in fact, it doesn't only hold for the first n cycles, it holds for infinitely many cycles, it holds forever. This is what we would like to do. In most cases, we would like to do that something holds forever. However, in some cases with very complex designs, this can be hard to achieve. Then you are in troubles if you would like to prove that your design is correct under all circumstances. But if you are, for example, bug hunting, you could still say, well, a bounded model check for 100 cycles gives me enough confidence that actually this design is correct and works as expected. Because of my understanding of my design, I know within 100 circles it should reach all the reachable states anyways. So when you run it, you get this output. And the first one is for the bounded model check. So we just check, are the assertions, hold the assertions in time step 0. Then after one state transition, do they hold in state 1, and so on until we reached state 19. And the other one is the induction step. And the induction step counts backwards from 20. And if it's very easy to prove something by induction, I will talk a little bit more about this later in the presentation, then this will maybe try to improve induction in step 20 and then in step 19, and we'll say, well, it passed, everything is okay. In this case, it's a little bit harder, and we need to go down all the way to step 15 before the induction works. And we will see a little bit later why this is. Okay, so who here knows a little bit of Verilog? Oh, that's good. It's at least maybe 30%, maybe half of you. That's great. So for formal verification, you need to have some additional statements in the Verilog language. Namely, you need to have a way to create assertions, and you need a way to create assumptions. And we've seen those assert and assume statements already in the Hello World example I just showed you before. So when you have assert some expression, it just says, we say this expression must always be true. And if there is a way to make this expression false, then this is a bug, and the tool should tell us how to get into this state, should demonstrate the reachability of this bug to us. And assume, we also say this expression is always true, but we don't say it's an inherent property of the design. We say this is something we restrict our proof to. So in some cases, you might say, we assume that this input signal is only always low, or we assume that those two input signals are never high at the same time, maybe because this is some kind of a protocol, and we assume that the other side of the protocol, the peer we talk this protocol to, is using the protocol correctly, and maybe in this protocol, those two signals can't be asserted at the same time. Restrict for verification essentially does the same thing. We say we don't want to consider traces where this expression is false. We only want to consider traces where this expression is true. However, there is a little difference in the circumstances when you use assume and when you use restrict. And assume you use when your assertions depend on it. When you say, well, if this assumption doesn't hold, then I really don't care about the assertions, because I know if, for example, these two lines are asserted both at the same time, then my core will go into some crazy state, because I wrote my core under the assumption that the peer I'm talking this protocol to will actually adhere to the protocol specification. With restriction, we essentially say, this makes the proof easier, if we assume this expression, but it's not really necessary for our assertions to hold. And because of that, when an assumption is violated, simulation will also produce an error. But when a restriction is violated in simulation, then we don't care, because we've said the assertions don't really depend on it. It's just an additional thing for formal verification. that makes the proof a little bit easier. There are immediate assertions and concurrent assertions in Verilog. So immediate assertions are within a behavioral block like initial or always. And there we can use assume and assert like a normal statement. Concurrent assertions are used in module context and essentially assume or assert that something will hold forever in all states. Whereas in the behavioral part, we could use an if statement to add an a condition to an assertion or an assumption, and then this assertion assumption would only need to be true when the if statement also works. Usually, the concurrent assertions in Verilog are used with system Verilog properties that can be temporal properties, but right now Yosys doesn't support any of that. And because of that, we could say when we are using Yosys, when we are using this flow, then usually we will use immediate assertions within a behavioral block like initial or always. Okay. Formal test benches. So in simulation, we usually have a test bench that creates input signals for our circuit and stuff like that. With formal verification, we also sometimes use test benches. However, those test benches don't play through one possible path with our circuits like a normal simulation test bench does. Instead, we just add some external restrictions or assumptions for stuff like, well, reset should be low in the first cycle, things like that. But other than that, we leave a lot of free room for the verification tool to actually explore different parts and see if using the thing in the formal test bench, it can reach an invalid state. So this is a variation of the design we had before, the Hello World design, but now using a formal test bench. You see I've removed the initialization for the counter. So now we only have these always blocks where we say, well, if reset is high, then we set count to 0. Otherwise, we increment count. And in our formal test bench on the right, we assume that the reset signal will be high initially in the first cycle. So because of that, we reset the design from outside from the test bench in the first cycle. And then we have the same assumption and assertion combination we had before, but now with a condition around it that we don't check it in the initial state. So in the initial state, we don't care what count is because it can be anything. We just wait for the reset to complete, and after the reset has completed, when we're not in the initial state anymore, then we actually apply our assumption and assertion. Okay, this is a slide I thought I removed. Oh. 5 minutes extra. Yeah. So bounded and unbounded methods. This is terminology we'll hear a lot when reading or talking about a formal method. A bounded method essentially says we check that the property holds within the first n time steps. And we had this before here when I just call Yosys SMTBMC without this -i parameter, then we run a bounded model check for 20 cycles. And an unbounded method is we would like to prove that the property holds forever and not only for a limited number of cycles after the initial state. So BMC, which is part of the Yosys-SMTBMC name, is a bounded model check. That's a bounded method. And temporal induction is a mechanism that builds in a way on a bounded model check and extends the validity of the check for forever. Let's have a look how we can do that. That's the bounded model check. So we create a formal circuit within our tool that more or less looks like the example at the top here, we have an initial state in yellow, and then 3 states that follow the initial state. These are the green states here. And for each of those 4 states, we check if all the assertions hold. So this is the naive way of creating a bounded model check. Remember, this now are like formal states, they're like variables, they're like placeholders for all the states that are possible. The only thing that we constrain is the first one should be a yellow one, it should be an initial state, and the others don't need to be initial states. They're only constrained that there must be a valid state that can follow after an initial state in case of the second and so on. And this works. So this is a correct way of making a bounded model check for n equals 3 time steps. But it's not very efficient. And in practice, it turns out it's much more efficient to use the scheme on the bottom half of the slide. We first just create a symbolic initial state. So a symbolic state that can represent any initial state. And we check, is there any initial state that violates one of my assertions? And if there is such an initial state, then we are done. I just output this state and say, well, obviously this initial state violates your assertions. So this is your counterexample. If this does not succeed in the way for the tool, because the tool would like to find the bug. So the tool doesn't find the bug here. We figure out that all the initial states actually conform to the assertions. Then we create a formal model for 2 states. And now we can assume that all the assertions in the first state will hold, because that's what we just proved in the first state. Yeah, and so on. So if we find something here, we output a counterexample that's 2 cycles deep. If it doesn't count, well, we move on to the next state, next step, and make a proof that's 3 cycles deep, and so forth. And in practice, this turns out to be much, much more efficient than the naive approach where I would like to prove like everything at once, especially if you would like to do a deep bounded model check that's like 100 cycles deep, something like that. So temporal induction now takes one of those bounded model checks. So now we have one of those bounded model checks above. It's the naive implementation, but this really doesn't matter here. And then we create the proof that you see in the middle of the slide here. So initially we say there is an initial state followed by 3 other states, and none of them violates any assertions, and we have proven that. And now we would like to prove that when there are 3 states consecutive that don't violate assertion, then there is no way for a first state to violate assertion. And if this works, if we can prove this, we have obviously proven that the assertions will hold forever, because this here kind of fits together. So we can just say, well, we have proven 1, 2, 3 non-initial states. So this exists. And if this proof holds, we know every state that follows the third state here must also conform with our assertions. And then I just take this proof that I have made, and I don't need to change this proof. I don't need to rerun this proof. Just think of moving this 1 step to the right, and I can apply the same argument again and again and again, and therefore I have proven that my properties will hold forever. So this is great. However, it doesn't always work. So if this kind of thing works and tells us, well, your design seems to be fine, then everything is good. But this might tell us I can't do this. I can't do this proof. I find a counterexample. And now this counterexample can mean, well, maybe my assertions are violated somewhere deeper in the state space. Or it can mean, well, maybe maybe everything is correct, but I just need a deeper induction proof. Maybe it doesn't work with 3 time steps. Maybe it only works with 20 or 100. Or maybe it doesn't work at all. And that's what we see in this picture here. So here again, we have the states that violate assertions in red. Then we have all the reachable states in this bubble here. So if you look at the direction of the arrows, you see there is no arrow going out from this inner bubble to the outer bubble. So these actually are the reachable states in the system. However, usually we don't have an explicit representation, an explicit picture like this of all the reachable states. And then we have this, this intermediate zone here, where there are states that are okay with our assertions, but nevertheless are unreachable. And when we look at this proof that we are trying to do, this here, we don't know if these states are reachable or not. So we could, for example, find here 1, 2, 3 states that are okay with our assertions, followed by a state that's not okay with our assertions. So if we find something like that, the easiest thing we can do, we can increment the induction length. So here we need at least 5 consecutive states, because 4 are there. But if we say we have proven for 5 consecutive states that are okay with our assertions, then we won't get a counterexample here. However, we might get a counterexample here. Why? Because there is a loop. And in this loop, I can fit an arbitrarily long sequence of states that are all okay with my assertions. And then in the end, I break out and reach this state here. So here, I can't just make the induction longer. I have to use something else. For example, I have to add an additional assertion to my design that invalidates one of those 4 states that built the loop. And if I do this, then I can prove this example by induction, because I don't have this loop there anymore. When you would like to do this, when you would like to make such a proof, this is the entire flow you'd be using. You take your Verilog design, your assertions, you put them through Yosys. Yosys generates an SMT tulip model. Then we put this into Yosys SMTBMC together with an external constraints file, pass it to the SMT solver, and then I get a pass-fail information. And if it failed, I get a counterexample with a VCD file or a Verilog test bench that reproduces the counterexample, or a constraints file that I could put back in on the left side. For example, if I would like to just easily reproduce a thing that I found before. So the typical workflow would be, we first run a bounded model check. That's the easy part. We say, for 10 steps, for 20 steps, see if you can find a violation of my assertions within 10 or 20 steps. And if this fails, then we know we have a bug. We know we either have a bug or one of our assertions is bogus. This is, of course, also an option. So the solution is either fix the bug or add additional assumptions or loosen the assertions so that everything is right. If this passes, then we move on to step 2. And step 2 is this temporal induction step. And if that fails, then we have to investigate the counterexample we get and make a decision. Is this reachable, what the solver is showing us, or is this not reachable? This is our judgment call, essentially. And if it's reachable, then the same thing as before. We have to fix the design, we have to add assumption, or we have to loosen assertions. However, if it's unreachable, then we have to add additional assertions, usually, to tell the solver that this is actually an unreachable state. And that's the kind of dialogue you have with this tool while formally verifying something. The solver is giving you a counterexample, and you have to explain to the solver, well, that's actually not reachable because this condition will never become true. And then the solver will probably give you another counterexample and so forth. The nice thing about this is, when it passes, we know everything is right, but we still have 2 options. We can say we are fine with the thing we have. We have proven that our design passes verification. We are done. But we could also say, I would like to have more assertions in my design. And then I just reduce the induction length. And I will get another counterexample now for induction with a smaller induction length. But now I will know that every counterexample I get is unreachable, and it's much, much easier to work with this. And if I make a mistake and then add an assertion while telling the solver that something is unreachable, well, the solver will then tell us, here's an assertion that can be violated using this path. So there is really nothing you can inherently do wrong. Yeah, the idea would be to talk about this flow again with this graphics, but I will skip it. So we have a variation of the design we had before. We have a counter again, but this time we have a mode input, and the mode input tells us if we should count up or if we should count down. And we assume that initially count is 5, and we assert that it can never be 200. And if we stare at this for a little while, we see this is true, because when the count is 99, we will not increment it any further. So there is no way to go from 5 to 200. Also, there is no way to do it with another underflow, because if the count is 0, we also don't decrement it anymore. And if we run this, the bounded model check will work. However, temporal induction will not work. It will give us a counterexample like this, where it starts with 194, and then increment and increment and increment and decrement. So it will do some things here really, really close to 200, and at the end of the counterexample, we say, and then I can increment from 199 to 200. Of course, the thing is, the reason why we get a counterexample like this is because we haven't really told the solver that count equals 194 is not reachable either. So if we modify our design like this, and we add an additional assertion where we say count is always smaller than 100, then the proof will work, and we will have proven that all these assertions actually hold. And because in the example I had first, I was only incrementing, and I was saying we can't reach step 10, but we assert, so we assume we don't reach step 10, and we assert we never reach step 15. Because of that, I had to have 15 steps in my temporal induction, 5 steps in my temporal induction proof from 15 to 20 in order to prove that. Now that we have correctly described the entire reachable state of our design, we can actually complete temporal induction within just one cycle. Okay, I have some other examples that I just would like to mention quickly now. There is a special command called assert pmux that adds additional assertions to your design whenever there is a parallel case statement. And in this example, we have a parallel case statement in Verilog. So we, as a designer, tell the tool that those two cases in the parallel case statement are exclusive, and the tool might use this information to do any optimizations. And if we are wrong about this thing that we say, well, the case statement is parallel, then we might run into evil problems, because we might, for example, test our design in an FPGA for many, many hours, and everything works fine. And it turns out the reason is because maybe this FPGA tool in this instance has ignored the parallel case. But then we go to an ASIC, for example, and we synthesize the same thing with the ASIC tool, and maybe the ASIC tool will actually use this parallel case to do an optimization, and then all these hours of testing we've done on an FPGA is completely worthless. But with a formal verification tool, we can, of course, prove stuff like that. That's another example. I have a memory design here. Then I have another memory design that's kind of convoluted, but sometimes code looks like this. Then you would like to force a synthesis tool to infer a special form of hardware resource. And we would like to prove that these two memories are equal. And if we do that, we create this kind of formal test bench that just instantiates both memories in parallel. And then we add this additional constraint file on the upper right, where we assume that in the initial state, the memories in those two instances are actually the same. And then for all the other states, we assert that they are still the same, and we also assert that they output the same value for the same input. And the input will be the same because the input ports are connected to the same top-level input. This is an example for using multiple clock domains with Yosys SMTBMC. So just to show you that this is something that's also possible. So here we have a counter, but we implement this counter just by using the lower bit we've just created as a clock input to another toggle flip-flop, and then we go on. So if you're building a counter from like TTL ICs, then this would be a possible way to build a counter. Usually you don't do this on a chip, because now we have 1, 2, 3, 4 different clock domains here. So the first always block is like the regular counter, and then the other 4 always blocks are the bits for our other counter. And then we assert these 2 counters, they must always have the same value. And indeed, I can prove this. I need the special command clock to fflogic to enable this, but then this can be done. Similarly, this is another design where I have a set reset flip-flop. Never use something like that in a real design. It's horrible. But if you have to use it for some reason, we can actually check here. And of course, this is actually what the Xilinx tools do for a set reset flip-flop, because they don't have it in a hardware resource. They create this weird thing with 2 flip-flops and the latch and the mux. And we can actually prove that this is the right thing to do, that this still is a flip-flop like this. Can also do custom things. I'm not going to talk about them. There is a larger project going on right now trying to do end-to-end formal verification of RISC-V processors. It's called RISC-V Formal. So I'm working on that right now, and this is also, of course, using a lot of this infrastructure to do this kind of verification. So if I would like to look into a more complex thing that can be done with formal verification and with this formal verification flow, then this would probably be worth a look. Future work. Well, I would like to add more system Verilog assertion properties support. This is just something that you will find a lot of existing code for formal verification tools, and it would be interesting to be able to use some of that with this flow as well. Then there is improved support for Verilog X propagation. So in some of my other formal verification flows, I can actually model Verilog X propagation exactly the way the Verilog LRM is specifying it. It would be interesting to also be able to do that with this flow. I have on my to-do list a C backend for Yosys. So you can take a circuit and convert into a flavor of C that is good for formal verification with C formal verification tools like C prover, SMTBMC, stuff like that. And also there is a project going on called Symbiosis, which is like a big front end to use all this Yosys-based formal verification flows without having to learn a new thing whenever you switch from one flow to another. That's it.
So what did we learn today, Clifford? What did we learn today? What did I learn today?
That I can speak very fast.
No, you were really quick. And something you do normally in half a day, you did in an hour. So that's fantastic.
Yeah.
We have some questions in the audience. I know there's one on the web. I will take this right now. No. That's disappointing, but we have some others. This man, please.
Yeah, I did not yet understand what is the difference between Yosys and just using like any kind of Verilog simulator. I mean, the simulators also react on asserts and whatnot.
Yeah, but you have to write a test bench that triggers the assertion. And with formal verification, you don't have to do that. You can just say, this is the set of valid inputs. There is a better way to do that.
We can do this in a minute.
So, when you go to that, with simulation, you just have individual traces that may or may not trigger your assertion. With this formal verification, you can have a tool that for you looks at the big picture, because I can't paint the big picture. I mean, this is a comic, but the state graph for a real-world circuit would probably have more states than the photons in the universe. So you can't really, yeah.
Someone else? Yes.
I'm wondering if in your experiments you have actually run into problems with vacuity? That your assertions hold because you have artificially restricted the state space too far?
Yeah, I mean, this is possible. Whenever you use restrict or assume, you have this risk that you've restricted it in a way so it doesn't really work anymore. So in a usual workflow, you often have some Verilog defines or whatever in your design that you can use to artificially add bugs. And then you always check that at least you still can find those bugs. Of course, this is not a guarantee, but at least it improves the situation a little bit.
Okay, a question there from out of space.
Yes, so what kind of expressions does Yosys support in these assertions?
Because essentially I only support immediate assertions. You can use like any Verilog expression, but it's not the system Verilog properties syntax that you could use to express temporal properties in system Verilog. Those are not supported right now.
One last question. This, sir?
Can you give me a rough idea of how long the formal verification needs?
It really, really depends on the kind of problem, on the solver you have, on many other parameters. So here I have a couple of solvers, 3 different benchmarks, and you see there is quite a span. And always, maybe this is not really can be seen here, but often you have an example that it works really, really well with one solver, but it takes a long time with another solver. But with a different problem, it's just vice versa. And because of that, it's really good that we can use Yosys SMTBMC with almost every SMT2 solver.
Thank you.
Okay, thank you, Clifford. It's really fantastic to have you here, and really the will that you're sharing your knowledge, your explorations with all these people. Give him another applause, please.
Thank you.
Him.